Awesome. So let me figure out how the screen sharing is going to work. That is the correct one. Share. All right. Can everyone see my screen, but not my speaker notes?
Yes.
Awesome. Cool. So I'm going to make sure that I can vaguely look in the direction of the camera. So I'm not talking to you while staring over in this direction. But so yeah, I'm going to be talking about type checkers and which ones you should be using with your Python. Just a little bit of an intro to me. My name is Rami. I go by Necaris on the internet. You can find me on GitHub or on Twitter under Necaris. And I'm currently working at a company called Coiled, which helps organizations scale their use of Python. So if you use Python particularly for data stuff and you want to scale that, come talk to me or message me or whatever. This whole virtual thing has got me all flummoxed. So I'm going to be talking about type checkers and which ones you should use with your Python. Okay. What? So I'm starting with the assumption that everyone here has heard of the idea of putting type annotations, so indicating that a value or a variable is an integer or a string or something like that in your Python code. And you may even be on board with this idea. But just in case, I'm going to spend a couple of minutes on sort of what they are and why you might want to use them before I dive into the comparison. So syntax. What does this type annotation stuff look like? Well, so the early Python enhancement proposals, and for those who aren't familiar with them, I'm going to be calling them PEPs because I've been following them for a while. But a Python enhancement proposal, or a PEP, is basically a proposal to improve Python in some way, and that goes through a review process and gets approved. And then, lo and behold, at some future point, it will be in the Python language that we all know and love. So PEP 3107, which was one of the Python 3.0 PEPs, and was implemented actually, when Python 3.0 came out, allowed any arbitrary annotations on a function's arguments and return values, right? So it was literally anything. One of the examples that came with the enhancement proposal, in addition to type annotations, was documentation strings, for example. Then PEP 484 focused the annotations a little more on the specific use case of type hinting. And that landed in Python 3.5. So since then, it's really sort of been understood that you can annotate your variables with whatever you want by putting a colon after the name of the variable and whatever annotation you want after that. But those annotations are really supposed to be type annotations. So more recent versions of Python, particularly Python 3.6 and up, implement a more recent enhancement proposal called PEP 526. And that actually opened up this whole type hinting syntax even further. No longer are you limited to this having to be on your functions. You can use these type annotations on pretty much any variable. So over here, we can see that we have primes, which is a top-level variable in the script. It is defined as a list of integers, and it defaults to an empty list. We have captain, which is just a string. I'm sorry.
Is that, do I need to mute someone, Ron?
I don't know. Is someone trying to ask a question? I can't really hear.
I think we just need to mute everyone.
Yeah, let me try to take care of it. Sorry.
So I just want to, now that I've gotten it, I just want to show a couple things, right? So we're going to use.
Does anyone know how to do that on Zoom?
Off the top of my head, I don't.
So let's look at.
It's Al. Al is not muted right
So
now.
I've got a couple places
Owl?
Al Mercado.
Okay.
Oh, there he is. We muted. Thank you.
All right, cool. Sorry about that, Rami.
Yeah, no worries. So we have our variable captain here, which is annotated as a string. Note, we didn't even have to put an initial value on it. And we have our Starship class, and we can see that the stats attribute on the Starship class is annotated as it's going to be a dictionary mapping strings to integers. The typing library that you can see importing here, that's part of the standard library, again, as of more recent versions of Python 3.5 and up. And that is what defines these nice generics like list with a capital L or dict with a capital D that let you sort of parameterize and narrow down your type annotations. Okay, so what are we supposed to do with all of these exciting type annotations? Okay, well, I'll give you an example. Suppose we have some code. This is a fairly dumb example. So we can see right away that if you ran that code, you would be calling the split function, you'd be passing it a couple of integers, it's expecting a couple of strings, and it's calling the split method on the strings that it's expecting. And so, you know what? This is not going to work. This is going to fail with an attribute error pretty quickly. And that's not great. But if you were to run a type checker, rather than failing at runtime, so in this case, I'm using MyPy and say MyPy dum.py. And rather than failing at runtime, we see this failure right here. And I don't know, is that text big enough for most people? Cool. So rather than failing at runtime, we see the failure right there. We can fix it before we ship our code anywhere where it might cause us problems like embarrassment or lost money or other things that people code for, right? But my beautiful Python, you might say. And I sympathize, okay? I know this feeling. One of the things that I personally enjoy about getting to write Python code is this simple, elegant syntax. And all of these parameterized type annotations anywhere don't really match what I'm used to thinking of as beautiful code. And this is a particularly egregious example that I've put up here, but it's not completely out of the realm of possibility. But there's two things that really help me appreciate the type checking nonetheless. One of which is that none of this is in the least bit mandatory, right? So PEP 526, which is the most recent PEP that's relevant, explicitly puts this in as an anti-goal. They're saying by no means is this ever going to be required. And we can see an example here of, here's some code. It's not annotated at all, but we're checking the special magical sort of variable here, typing.type checking, which is a special magical variable that's only true when you're running the type checker. And we're asking the type checker to call, again, the special magical function, reveal type, to tell us, hey, what type have you detected for this banner function? And so if you use, in this case, I'm using another type checker called Pyar. If we run it over this script, there's a bunch of output, but we can see that part of the output is the output of reveal type. And reveal type is telling us that the type of the banner function has been detected as returning a string and taking a single argument called year. And so we know that, hey, Pyar at least is able to infer a bunch of stuff about our code without us having to annotate anything. So we can still actually get some value out of running our type checker even without having to uglify our Python. The other thing is also, one of the things that I used to love when I first started writing software was just the elegance of the code and the stuff that I would see in front of me. And honestly, I at least have come to value a lot of the abilities that the code gives me or gives my coworkers or my team members as much or more than just the beautiful code in front of me. And so being able to give my tools, like my IDE, hints that they can interpret is incredibly powerful. And there's that deeper elegance that I've come to appreciate to clear and usable code. Just as an aside, the screenshot that I have here is from Visual Studio Code with the absolute most basic configuration. I'm sure that you can actually get even more detailed output from Visual Studio Code. I don't actually use it. I just put a screenshot up there for a tool people might be more comfortable with than the tool that I usually use, which is Emacs. So let's say, okay, you're convinced by my impassioned and elaborate spiel, and you think, okay, let's give it a shot. Let's try this type checking work. How are we going to do it? Well, we have lots of options. I was told once by someone I used to work with that most big Python shops, most companies that use a lot of Python, needed to come up with something to type check their code as part of their transition from Python 2 to Python 3. And several of these solutions have been released as open source, so we kind of get our pick, which is really nice. I'll talk about them each in turn, but we have options produced by Dropbox, called MyPy, by Google, called PyType, from Microsoft, which is called Pyrite, and from Facebook, which is called Pyar. Now, I did a bake-off of these tools against each other for my particular use case last month, and I wrote it up. That was actually the basis for this talk, is a blog post that I wrote, and the URL is at the end with the slides. But this is sort of the environment from which I ran these tests. I have a fresh content environment using Python 3.8. I have a checkout of a small but not trivial project, in this case, the Zict library from Dask. It's about 650 lines of code, so it's small, but it's not completely trivial, and is probably about the size of maybe some of the smaller projects some of us are working with, so it's kind of realistic. I also added a little sample script with a number of errors that I'd expect a type checker to find. So we've got the part one here. We'll refer back to this and to the class in the next slide, but quickly, there's a couple of obvious errors. So here we have, for example, the obvious annotated error function, which is taking an integer, it's trying to concatenate it to a string. That's going to fail with a type error. And a couple of less obvious ones, with and without annotations. So for example, unannotated error here takes an input called I. It calls innocuous helper on it on the integerization of I, and innocuous helper is expecting a string and calls split on it. So I'd expect a type checker to infer enough about my code to go, hey, that's going to fail. Don't call unannotated error with basically anything. And we have something even more elaborate in ambiguous returning helper, which is called from less obvious error and relies on your type checker being able to tell that found may be none. And so when you call ambiguous returning helper, you may get none back instead of the string that you're expecting. And so when you call upper on it, it's going to fall down hard. There's also this class, which I put together sort of as a demo. It's very short, but it's not completely atypical of Python code that I've seen. Basically, can the type checker handle this? We have a list of callbacks. They may or may not be callable as functions. It could be none, which is the default value, and we're actually calling those callbacks and returning a generator. So there's a bunch of stuff going on, which is slightly medium to advanced Python usage. And if a type checker can't handle this, then it's not going to be great for a lot of the Python code that we write on a regular basis. Cool. So all that aside, let's dive in. Let's talk about the type checkers. MyPy is probably the first project that comes to mind when you think of typing and Python, and that's with good reason, because the development of MyPy when Guido was working at Dropbox helped to drive a lot of the discussions and the peps around typing in Python. It's still very actively developed. There are lots of conference talks about it, and it kind of benefits from the halo effect of being associated with Guido and Dropbox. So it's certainly a solid choice. So start off, how do you configure MyPy? How do you make sure that it runs correctly? Well, no configuration is actually necessary. Running MyPy is as simple as pip install MyPy followed by MyPy sample.py, for example. But you can put configuration in your setup.config or add a mypy.ini file. Honestly, when I was running the tests over the Zict project, which I checked out, the Zict project has a test subdirectory within it, which is a perfectly common way to organize your tests. And I couldn't find a way to ignore that subdirectory, so you might end up running it over your tests too. You also probably want this command line flag, ignore missing imports, to get started with, because otherwise MyPy will complain about not having type information for every library you've ever imported. So speed. This is where I actually start to reveal one of my concerns, which is very much what Aru was talking about in his question to Mike. I use pre-commit as well. I think it's a super cool tool. I'm really glad that Mike talked about it. And I like to have checks like linters and my type checker run in my pre-commit hook. And so if I'm running something like a type checker in a pre-commit hook, I want it to be really fast. I want it not to be a giant pain in the butt to commit. MyPy, in this case, running completely from scratch all over this small project, took well under a second. Hey, that's actually fine for me. There's also, if you want incremental sort of type checking goodness, there's a long-running daemon mode. And there are also plugins for language servers. So if you're familiar with language servers, there are projects like PyLS or whatever that actually run in the background and provide incremental information about your Python code, and they work really tightly with IDEs like Visual Studio Code. And MyPy has plugins for that that allow you to just incrementally get all of the information you might want, which is nice. However, there's a downside, at least for me and for my use case. And that downside is that MyPy kind of falls down on accuracy and useful errors. So without any options, I'm just saying MyPy run over sample.py. I'm expecting it to find that all three of the functions defined in sample.py have errors. And it only finds one of them. It finds the really obvious annotated one where I said, well, this is taking an integer. And it says, well, you're concatenating an integer and a string. It's not going to work. OK. So maybe there's another way. MyPy supports a -- strict option. Let's try it, in super strict mode. Nope, it doesn't catch any more errors, but it does demand that I annotate my functions all over the place with type annotations. Okay, that's not as helpful as it could be, but it certainly already caught one error, so there's some value in it, no matter what. Our next option comes from Google. It's called PyType. And as you can tell, by the time I wrote this slide, I was rushed enough that I didn't write the fancy, sliding in of every single bullet point. So apologies, from this point forward, it's going to be slightly less fancy. But PyType is sponsored by Google. It's been mentioned at conferences. There's some tutorials. It's not as commonly spoken about as MyPy. It's not the sort of reference implementation. But the documentation website is really quite thorough, and I actually quite like it. Configuration. So just like MyPy, you can just type pytype sample.py, and it'll just work. In order to get it to do things like ignore your test files, you do need a configuration file. So by default, this is pytype.config, and you can call the -- generate config option to generate one, but it'll also read your setup.config if you've got one. However, the downside is you can use a configuration file and be precise about, let's say, ignoring test directories, but then you have to configure everything else as well, including where your code is located to look for it to type check. There's also a command line option, keep going, which I recommend running no matter what, because otherwise it will fail on the first type error that it finds, and you won't actually get a full report. And just for completeness, here's an example of my pytype.config. You can see it's in the ini file format, which setup.config and other things are written in, but it's fairly straightforward. There's only a couple of options that are required. And here you can see I'm just trying to exclude all these things that are not relevant. I say, okay, go look in the Zict subdirectory for inputs and keep going past errors. Analyze as many files as possible. So far, so good, right? What is wrong with PyType? Absolutely nothing, except that it's really slow. So that's by far the biggest issue that I have is on this small project, it's slow enough that if I had to run this afresh every commit, I would be really annoyed. This takes almost 6 seconds on a relatively small project. It does have sort of nice incremental checks, so subsequent runs are faster and they're well under a second, but I've also found that they're kind of flaky. Occasionally PyType generates flaky results and I have to clear out the cache directory and rerun it from scratch. So I can't entirely shake that mistrust of incremental builds, which means that I'm stuck with the full fat sort of slow version. And personally, I don't know that I could do that to myself. But I talked about kind of a con, but here's the pro that outweighs that. This caught all three of the actual errors in my sample script. It even has partial traceback sort of pointing out where the error is going to occur. It says, for example, on that very first, the obvious one, hey, you're adding strings and integers, they're unsupported. Innocuous helper here is going to be called with an integer, and it's called from unannotated error. And and that's not going to support that split method. And less obvious error may get none as a result, and there's no upper method available on that. So there's ways to track down all those errors, and PyType is actually doing a really good job of reporting them. And also, the all kinds of dynamic class that we had looked complicated, but PyType went, yeah, that'll probably work, and skipped right past it, which is what we wanted. So far, so good. There's also an extra, which is PyType comes with a merge PYI script. And so just a step back. With typed annotated Python, you have two options. You can either write type annotations right in your Python code, or next to or in some defined location, you can have .pyi files, which are sort of type stubs for your Python code. And so, for example, if you're working with a third-party library that doesn't have type annotations, you can write the PYI file yourself and tell your type checker what types to expect from that third-party library. When PyType runs, it actually automatically generates those for you. And you can use this merge PYI script to merge the PYI type stub files that it created for you right back into your code. So you can have it auto-annotate your code. And that's really cool. Finally, we have our friend from Facebook. Facebook's Pyar only has the one conference talk that I could find. And all over its website, it talks about performance. It's quite a nice website, and it's supposedly the fastest type checker that anyone's ever made. So that's kind of exciting. I've also been accused of being overly excited by things like this, but Pyar has another cool fact, which is that it's a real-world OCaml project. OCaml is a programming language you don't see a ton of around these days, or really any days. And so the fact that Pyar is written in OCaml and is a real sort of OCaml project, that's kind of interesting. I also just really
In case
like
you're curious, Rami, there is an OCaml linter for pre-commit.
Oh, hey, sweet.
I just checked.
No. Thanks, Mike. I didn't know that. That is awesome. So yeah, so if you want to contribute to Pyar, you can have pre-commit lint your OCaml code. You should do that. Pyar actually does require a configuration file. You can't run it just, pyar sample.py, but it has this handy pyar init command to generate it, and it's JSON formatted. And honestly, it took me a little fiddling with this configuration file to get it to run without throwing a whole bunch of spurious undefined import errors. And it also looks like the only way to silence them is to add an ignore comment to all of the affected files. So I didn't find the configuration super intuitive. And again, just for completeness, here it is. This is pretty much automatically generated, and then I filled with it a little bit. So, there's a bunch of things that I don't really understand. I'm basically kind of leaving well enough alone. Again, not the most intuitive or well-documented of configurations. For an initial run, this is from nothing. This is barely fast enough for me to want to run in a pre-commit hook. Sure, it's a lot faster than PyType, but it's way slower than MyPy. It's more than twice as slow as MyPy. There is an incremental command, so you can run pyar incremental, and that'll spin up a server in the background, and that will work with the language server protocol that I mentioned earlier with Visual Studio Code or Nuclide, which is Facebook's sort of preferred editor. And it'll incrementally run additional checks and watch your code and make sure that you get updates. I will confess, I didn't manage to get it to work, but that's probably partly because I don't really use either Visual Studio Code or Nuclide, so your mileage may vary. Accuracy. All right, so hey, Pyar check. It gives me this cool little lambda icon and says I found a type error. Unfortunately, it's only the one type error that MyPy also found, and there isn't really more to that. However, Pyar has some sort of niceties that come along with it. It has a bunch of subcommands that have sort of variety and personality. So if you are trying to do verbose debugging, you type pyar rage, which I thought was really fun. And there's also a pyar infer subcommand, and pyar infer is really cool because it's that merge PYI command from PyType, but all in one step. So you don't have to run PyType, have it generate some PYI files, go hunt those down, and then tell merge PYI, hey, merge these files over here with this code over here. Pyar infer will just do that in one step. It will, just like some of the auto-fixing linters that Mike mentioned in the last talk, it'll auto-annotate your code, which is really cool. That's really sort of like it for Pyar for me. Finally, we have sort of the final contender, which is Microsoft's comment, and it's also not even written in Python. It's written in TypeScript. So, if you want to install Pyrite, unlike all of the other tools, all the other tools are pip installable. Pyrite is not. It is a TypeScript project through and through. You have to npm install it, but there is a pre-commit friendly repo for it, so you can just install it into your pre-commit config and not have to have an npm configuration package.json anything in your code if you don't want to. Pyrite actually came out of Visual Studio Code. It came out of some of the automatic static analysis features in there. I personally really like it. I think it's really well done. Just like the first couple of options, you don't need a configuration, but Pyrite config.json, again, it's a JSON formatted configuration, is what you get. It has a ton of options. They're all pretty well documented. And if you wanted to, let's say, exclude your test directories, you did need a config file. Also a warning, folks at a previous company that I worked at and used Pyrite at found that if your virtual environment happens to be sitting next to your code, let's say you have a VN subdirectory or something, which I know many people do, Pyrite will want to try and type check your entire virtual environment and your entire Python standard library. And that's crazy. So that sort of has biased me towards being really explicit and saying, go ahead, like explicitly use a configuration, even though it's not strictly speaking necessary, and be sure to explicitly include and exclude the directories that you care about. And again, for completeness, here's my Pyrite config. Cool. So again, talking about speed, talking about the convenience of running this, Pyrite is pretty good. It's barely over a second for a fresh run. There's a -- watch option for a long running process. It looks pretty good. But if you look at this again, you might see a problem. And that problem is actually accuracy. It's limited in working with more dynamic Python. As we can tell, this Zict project, it's fairly small. None of the other type checkers had serious issues with it, but Pyrite is saying unknown is not iterable and all kinds of other things which are a little hard to parse. Also, when we run it over our sample.py script, it finds that first error, just like the others, and it finds a spurious error in our all kinds of dynamic class. It says that self.callbacks, which is our list of callbacks, is not iterable. It's unknown. But as we saw, none of the other type checkers had an issue with it, and we went through it, and we can hold on. I'm just going to go back to it. Go back to our self.callbacks script. 1 second. So if we go look at this code, we can see that our self.callbacks value, it's pretty much always going to be a list. It's not going to be unknown. So why is Pyrite complaining about it? I honestly don't know. If you tend not to write particularly dynamic Python, it may work perfectly for you and you won't have these issues. I ran into that a couple of times, but honestly, my code tends to be a little cleverer than maybe it should be. So make of that what you will. I gotta find my my spot again. Cool. So I've talked a lot about a bunch of different type checkers, and I've probably bored a bunch of you to tears, and I apologize in advance. Well, I apologize retroactively for that. But what is the one slide that I should have put up at the very beginning? The TLDR. One, use type annotations and type checkers. They will help. They will find errors before, before you notice them. And it's always good to find errors through testing or through CI or through other tools. I suggest using PyType, and I suggest using it in your CI environment because PyType is good, it's thorough. You can run it just like the pre-commit over all your files. You can run it over your entire project. You probably do want to run it in CI because it'll take anywhere from 6 to 30 seconds. On my current code base at work, it takes over a minute, and it's not a particularly big code base. So, you do want to do it in your CI. It'll drive you crazy if you do it in a commit hook. But if you want to be super safe and super careful, you can also use Pywrite and run that in a commit hook, and that will keep your code nice and clean. That's really it for me. Thank you for listening. I'll share these slides as well. The blog post that I wrote, the URL is right there. I recommend reading it because I personally find text and code samples easier to refer to when they're in a browser instead of my having to try and transcribe them off some guy's slides. You can find me on the internet as Necaris. You can find my website at necaris.net. You can find me on Meetup virtually or in person, usually at PyDistrict. Thank you for listening. Any questions, comments, wisecracks? I welcome them.
Have you found any disparities where your local, I guess in this case you're using Pywrite locally in your pre-commit hook, where it catches things that PyType wouldn't, or?
I have found that. So like I said, with the spurious errors sometimes, I've more often found that Pywrite comes up with an error that PyType assures me is not an error. Then I go back and look at the code, and indeed it's not an error. And so I have to tell Pywrite to shush. But there have been 1 or 2 times when PyType hasn't caught an error and Pywrite has. So I found that sort of belts and suspenders approach is sometimes useful. Yeah, again, your mileage may vary.
So I think Aru's question was kind of what I had in mind, which is, do you run both of these at the same time and they complement each other? Like, is that something that happens from time to time that you rely on them to complement each other?
Yeah, absolutely. Well, so typically, so I don't have this running right now. I did at a previous job. I have Pywrite set up with pre-commit to run in my commit hook because it's nice and fast and reasonably accurate. And I have PyType set up in my CI environment. So there are, something like 2/3 of things I found that Pywrite would catch, and PyType would catch some of the other things that, also resulted in failing unit tests or whatever. And so I'm glad I had them both. But if you're only going to use one, I would say use PyType because it will generally catch everything. And it's been a very small subset of things that I found that Pywrite caught and PyType did. Cool. Okay.